All right. Good morning, everyone. So today, I had planned to go on and work on this robbery optimization puzzle on Code and Game, and we might just do that. But last night, I saw a tweet by Dash Bark Dashiell. That's an interesting name. Asking for help with some kind of a math problem. So let's take a look at this. I thought it would be fun to try to solve it because I think, might be wrong, but I think it is relatively easy to solve. So she's saying, I'm dealing with what I believe is a linear programming problem. However, I'm not sure. I'm having trouble figuring out what my constraints are and my objective function. If I have a given set of ingredients, let's say apples and chicken, how much of each ingredient should I eat to get as close as possible to my nutrient goals? Fat 20, protein 22, carbs 10. And she gives examples here and goes on into what she's tried to do to solve this using math and whatever objective functions are. See, when I saw this, I saw the problem, right? You've got a set of parameters and an ideal state that you're trying to get at, and you want to find what combination of parameters will get you to that ideal state. And my mind automatically went to some kind of brute force algorithm or some kind of stochastic algorithm, something that just uses the computer's power instead of trying to figure out a formula. that's how I roll. And I think it would, the problem with brute force algorithms is that when you get a lot of different parameters and the set is unlimited, then it gets into this like crazy combinatorial problem, and it can take your computer years to figure it out. But in this particular instance, I think we can kind of, using just common sense, we can kind of restrain the possibilities for our parameters and limit it anyways, right? Like we know we can't have negative a negative value in terms of the weight of our apples or chicken, and also they can't have like negative protein. So that's good. We're starting at 0, right? So we can cap 0 as the minimal input. And there's also a logical, just common sense maximum too, that it won't make sense to test over that, because we'll be, for instance, if we're trying to get to a protein 22, well, we're not going to test weights of chicken where we'd end up with more than protein 22. That's just, or maybe like twice that, whatever, we'll figure it out. But what I'm saying is, I think there's a way to constrain this to a finite set of options, and therefore the computer should quickly be able to go through all of these and tell us which one's the best. That's my thinking right now. Anyways, I might be totally wrong. So let's try this. Let me just put that on the side. I'm going to need to keep an eye on this. And we could try to do this TDD. So I was thinking that we should have my headset's telling me it's running out of batteries. So if I can plug this in. There we go. Okay. So how are we going to set this up? I think I'm gonna use a class, so we're gonna call, let's say, we're just gonna call it the optimizer. Optimizer. It's gonna be a new instance of our macro nutrients, because that's what we're trying to optimize for. Macronutrients optimizer class. And let's see, so that I know what all our inputs are. I'm just gonna copy this here. This. How do I select one line? Control, no, Shift, End? Yeah, there you go. Okay. Okay, so we need, what do we have? We need to know our ideal, oh, I deleted that, didn't I? Nutrient goals, there you go. So we need to know what our nutrient goals are, and then we need ingredients. That's pretty much all we need. Then it's a matter of spewing out the weight of each ingredient that gets us as close as possible to our nutrient goal. So it would make sense to me to, when we instantiate this class, to pass in our nutrient goals. So let's do that. Nutrient goals. I could either pass an object, or that's what I was thinking, but yeah, let's do that. So we'll have protein. Let's do it in the same order she did. So fat, protein, carbs. Fat, 20, 22, 10. So 20, 22, and carbs, 10. Yep. So we're instantiating this. That's good. Let's implement this now. Export. Oh, actually here. Import. Whoa. What? Okay. Trigger happy. From main. Macro nutrients optimizer. Forgot my class. There, and we're taking a constructor. Constructor's gonna expect goals, nutrient goals. Is going to be should I do it with a type or should I do it with an interface? Nah, I'm gonna do it with a type. What was it again? Yeah, fat. It's going to be a number. And protein is going to be a number. Oh, I didn't set up TSLint, did I? We'll be fine. Constructor, nutrient. I don't think we'll need to access this from the outside. We don't want to, so private. Nutrient goals of type. Nutrient goals. Like that. Yep. Okay, so now, yep, this should transpile. And what are we going to do with this? We're going to call optimizer dot optimize, I guess. What are we going to pass to that thing? That's where we're going to pass our ingredients. Our ingredients, which will also have a fat, protein, and carbs content per 100 gram. Okay, how are we going to do this? I could simply... Yeah, so why don't we make this nutrients instead of nutrients gold. It'll be, let's call it macro because that's really what they are. Macronutrients. So optimizer is going to expect an array. And we're going to pass in, so let's do that here. Const ingredients. It's going to be an array. Then we're going to pass it here, ingredients. And how are we going to do this? We're going to use, well, we need the name, right? So this, let's make this an object, name, or just ingredient. Let's call this one apple. An apple. And then we need our macro nutrients. And let's be explicit, per 100 grams. Is it okay to use numbers in variable names? I think so. And use these here. 0, 1, 16. So fat 0. Protein 1. Carbs 16. We should probably type this. Do I want to make an interface or just a type? I feel like doing a type. We're going to call this ingredient. Ingredient. Ingredient's going to take, let's just grab this. This was pretty good. So ingredient's going to be a string. And then macronutrients per 100 grams is simply going to be of type macronutrients. Don't need this. So really this should probably be on one line. Yeah. It can be anyways. I don't know if it should, but it can. So let's type this just to make sure that we ingredient, it's an array of ingredient. Doesn't know where ingredient is coming from, of course. Export. In case we need this too. Now it knows. Thank you. So we're good. We're adhering to our type. So let's start with just the 1. See if we can solve just for 1. Optimizer dot optimize. Then you pass in the ingredients. That's what we want. And then the result of that should be the probably an array of ingredient name and weight. So we need an optimize method. Optimize. And it takes ingredients which are of type ingredient array, and we're returning should we return the entire ingredient thing? We're going to return an ingredient array, or well, we're going to return an array, I know that. An array of objects that have ingredient, string, and weight number. Let's use that for now.
2, 1, 2, 1, 2, 1, 2.
Yep.
1, 2.
Okay. So let's just return 0. Oh, right. Expecting. Let's return anything for now, because otherwise it won't compile. Well, first let's try to figure out what the correct answer to this would be. Now that's the kind of the complicated thing with doing test first for an algorithm like that, because the purpose of the algorithm is to find the answer, which is usually like a complicated answer to find by hand. But now we're trying to test that our algorithm is working. How are we supposed to do that if we don't know the answer ahead of time? Well, there's a good question. I don't know. But just for one ingredient, I think it would be pretty easy to kind of, or would it? I really don't know. Let's see, fat 0, protein 1, carb 16. Which one is the closest possibility? Now that I think about it, I don't see how we can actually do test first. This will be an interesting problem to explore some other time. For now, let's just try to implement a solution to this. Okay, so how are we going to do this? We've got our list of ingredients, and we want to find out which combination of ingredients and weight for each ingredient will give us, well, or at least will get us as close to our ideal state, which is our nutrient goals here. Now let's take into, I was going to say let's take for granted that we need to use each ingredient, but I don't think I'm going to do that. Let's let the algorithm go wild, and if it feels like the best option is to just give us one ingredient and nothing for the other ones, let's go with that. So how do we, okay, so the first thing we need to do is give the algorithm a way to know when it's reached the ideal state and how far away from the ideal state it is. So some kind of scoring function, I think, or fitness, I think, would be the official lingo term, whatever. So how do we do that? Well, we could just calculate the distance between, in grams, in total grams, from our result to the ideal state. Now, I don't know if fat or protein or carbs is more important, so we're just going to pretend that they're all equally important, and we're just going to calculate the total distance in grams from our goal, from our objective. And how are we going to do that? Oh, that I can test for. Okay. That I can test for. That's not too hard. Let's keep that here for now. Might need it later. So distance or score. Let's just call it, yeah, let's just call it calculate score. So we do need our ingredients, as we need something to, actually we don't. What we need is an output from const output. Probably rename that later, but basically we're outputting this here. So we should probably type this as well. Export type output. Ugh, that's an ugly name. What are we outputting? A combination of ingredients with their weights. What do we call that? Recipe? It's not really a recipe. Optimal ingredients, optimal ingredients. Yeah, whatever. Let's go with that. This will always be an array, so let's do it like that. Putting optimal ingredients here. Optimal ingredients, yeah. Main test output is of type optimal. I'm exporting it, okay. Optimal ingredients, which is an array. We've said it was an array, so let's go with that. An array of ingredient and weight. No. It's harder to reason about than I thought it would be. This is fine though, but that's not what we want to test. We need to test the composition of all this compared to so maybe we should pass in everything. Ingredient name. And then we'll have everything we need, I believe. So what we want, I'll fill this in later, but what we want, and this is, let's say, our goal. Our goal is simply of type macronutrients, right? Of type macronutrients. So it would be this here, right? Oops. And then we'd expect that when we're calling optimizer dot score. To be something. Okay, so for instance, if we were to have a list of optimal ingredients, what are we missing in here? Ingredient. Our ingredient should be an ingredient of type ingredient. Okay, so ingredient. Which is an object that has an ingredient name. Let's call this one, actually, let's get this. What else do we need in here? Ah, the weight. Pretty weight is missing from type, so that's where this is here, this is there. Got one too many brackets in here, I think. Don't I? This one goes here, this one goes there, this one goes here. Yeah, okay. So we're just missing our weight. And that's the thing, right? Okay. So if we're taking this example, forget this for now. We would be expecting our score to be, how far away from our goal are we, right? That's what we, well, we don't need to pass that in. The goal's already in the class through the constructor. So we would need, well, we're 20 away from the fat, so that's not good. We are 1 away, we're 21 away, so that's 41, and we're 6, so that's 47. We'd expect our score to be 47. So let's implement that. Optimize. Not optimize, score. Score is going to take output, which is optimal ingredients. That's a weird name. I don't think we... Let's call it recipe. Let's call it recipe. Or ingredient list. Nah. Let's call it recipe. It's not really a recipe because there's no instructions, but it's like a mix of ingredients. Mix of ingredients is the basis for a recipe, right? Score takes in a recipe. Recipe. And outputs a simple number. For now, let's forget about our optimize function. Oh yeah, this has changed now. We're calling this a recipe, right? Recipe. Recipe. And ideally, we want a score to be 0. That would be the ideal thing. Return 47. Let's cheat. I think I've set up. There we go. We passed. Yeah. That was easy. So let's add a test case. Calculate score with one ingredient. Calculate score with 2 ingredients. And let's change our goal just for kicks. Let's do this and that and this. And now let's change up our ingredients values to just whatever. Hey, thanks for following, Prophet. Okay. And let's change the weight. Oh, let's make it 200. It'll be easier. I gotta do this by hand. Okay, and let's add yep, like that. Just formatting my stuff properly. Nope. Get in there. Get in there. Okay, you go there. Yep. Like this. Just grab this. Gradient number 2, which we're going to call cow. It's got a lot of fat. Quite a bit of protein too. Very little carbs. Let's make it 100. Okay, so what's our score here? Whew. It's funny because the whole purpose of the program we're writing is so that we don't have to try to figure this stuff out by hand, but to make sure that the program is working, I got to figure it out by hand. Okay. Our goal here, well, let's make it the total first. So we've got, if we're looking at apples, our total is 10 fat, right? Because it's 5 fat per 100 grams. And we've got 200 grams, so 10. And then 18 in terms of proteins. And then 22 for carbs. And for our cow, we have 20 fat, 12 proteins, carbs, 3. Now, how far are we from our optimal? So that's a total of 30 fat, 30 proteins, and 25 carbs. What we were hoping for was 15 fats, so we're 15 away here. 7 proteins, we're at 30, so that's 23. And we wanted 25 carbs. No, we wanted 12, and we're at 25, so that's a 13 difference for a grand total of 36 plus 15, so that's 51. Our score is 51. So now we need to implement our actual algorithm here to calculate our scores. Basically what I've just done by hand. So first thing, what did I do? First thing is I added the value for each macronutrient. All right, so let's do that. We're taking in our recipe. Our recipe is an array, so we need to, I could use reduce for that, right? Reduce seems like a good thing to use. Previous, current, as per conventions. I will rename this in a second, but now what do we want to end up with? We want to end up with a, we're going to do the entire scoring thing in there. Yuck. I don't know that I want to do that. For now, let's just, well, we could, yeah, we could. Start with 0. All right, so what are we taking? What is P here? P is our number. It should be, yeah. What is V? When I say V, I meant C. C is ingredients and weight. Sorry. So I'm going to end up with like a loop inside of this. I don't think I want to do that. Nah. So instead, let's get our total macronutrients. That's what we should be getting. So fat 0. That's what we're going to initialize it to. Protein 0. And number, not number, carbs. Carbs 0. Mm-hmm. Right. Yep. Okay. C dot ingredient dot. Do we even care about the ingredient name at this point? No. What we need is this. Macronutrients. And then we get the carbs, we get the fat, we get the protein. Yes. So const macro nutrients. So we don't have to. Okay. And then we can simply go P dot carbs plus equals macronutrients dot carbs. Yep. And then P dot fat plus equals macronutrients dot fat, and then P dot protein plus equals macronutrients dot protein. Okay. And then we return. Oh, I can't do that, can I? Oh yeah, I can. I can mutate it. Why not? And then we return P. Do we need anything else than that? We don't, really. Oh, I've made a grave mistake. I need to take into account the weight, because this is the weight per 100 grams. So that weight divided by multiplied by 100. Is that right? So the carb, let's say we have 10 carbs per 100 grams, but we actually have a weight of 20, so we have 20 carbs. I would need to go 10 times 2 is what I would normally go to do, but how do I get to 2? Need to divide. It's the rule of 3, but for some reason I can't do it in my head, so got 10 carbs per 100, but I know I've got 200. So I need to times by 200 and divide by 100. That's what I need to do. So carbs times C dot weight. So let's skip that. Const weight equals C dot weight. Just do it like that. Divided by 100. That would be what we need to do. And that works. Do I need parentheses here? No. Okay. And now that gives us our const total total macro nutrients. And with that, we can simply go this dot nutrient goals and see how far away we are from how far away we are from it. How are we going to do that? I'm probably going to have to use math.abs. But first, total nutrients dot carbs Yeah, minus this dot nutrient goals, the carbs. That's where our math.abs comes in, right? The absolute value, that's correct, that's what we want. Then we just do the same thing with our fat. Oops. Fat and our protein. Okay. I could probably use a loop to do, but there's just 3 of them, so let's call this carbs difference. Oh, let's call it delta. It sounds mathy. Carbs delta. Yeah. Const fat delta. Const protein delta. And our score is the carbs delta plus the fat delta. Deltalat. Yeah, okay. Deltalat delta. Fat delta and protein delta. Let's run our tests and see how this totally doesn't work. Oh, or maybe it does because I'm a genius. Or extremely lucky and stumbled upon the correct output by total luck. Okay, so we got ourselves a scoring function, which I'm sure I can refactor later on to make it more concise and understandable, but not right now. Now we can use this to do what? We were trying to figure out which recipe was the optimal one, the closest one to our goals, nutrient goals. So we need to test. We need to test different possibilities. Okay, now we're getting into our optimize algorithm. Okay, so how are we gonna do this? Given a set of ingredients, so that is an ingredient name and macronutrients per 100 grams, we need to figure out the mix of those that will give us what we want. Well, the first thing is to figure out where to start, right? What weight to give to each ingredient. So how about we start by setting bounds for each weight? There's probably a way to set bounds for our weight. So let's, okay, first, it's pretty obvious to me that we're going to need to iterate through our ingredient list, right? But yeah, first, let's set up something that we're going to call ingredients weight bounds. And that's going to be an array. It's going to be an array that's going to take an ingredient name, which will be a string. Oh, well, typing it right now, but should be implementing it. So let's make this another type, I guess. Gradient weight bounds, maybe. And then we can just call it, well, no, that seems like, hold on. Let's just make it an empty array for now. We'll figure out the type as we go. But we know we want to fill that up with something that'll help us know where to start and where to end. So for const ingredients, ingredient of ingredients, we're going to take our ingredient dot ingredient name, yes, and we're going to let's make this array object. Hey, wait a minute, what's in our, what is that? It's a type ingredient. Ingredient has our ingredient name, and it has macronutrients per 100 grams. Okay, and that's what we're going to be able to use to set our weight bounds. Ingredient name and this is where it's going to be a bit more complicated. Weight. So we know that the bound's always going to be 0. We can't go below 0, so it makes no sense to test that. So ingredient max weight would be more what we're looking for here. Ingredients max weight. So this will be max weight. Now how do we determine that? For now, let's just make it very simple and use, let's see, if we, for instance, I think we can probably agree that if our goal for the total recipe is to get to 10 carbs, or let's say, okay, let's say to 20 fat, and chicken has 4 grams of fat per 100 grams of chicken, any recipe that has more than 20 grams of fat worth of chicken just wouldn't work. Doesn't make any sense at all to test for something that's over that. But then what happens when for instance here, apples, oh yeah, that's for 100 grams. We can have a recipe that has less than 100 grams. So yeah, let's just make our goal the maximum. We could even go just a little bit over. The important thing is to have a ceiling to this so that we don't, there's a cap to the computation that we're doing. So max weight, how do we calculate the max weight? The max weight is going to be equal to, what kind of operation are we going to do here? Well, we need to compare our goal and figure out, we're basically doing this right here, aren't we? We're essentially doing this here. Not quite though. Not quite. We need to start from our goal. We need to start from our goal. So let's just take carbs, for instance. This dot goal dot carbs minus ingredient dot macronutrients dot carbs, the carbs, but that's for 100 grams. We're interested to figure out how much of this we can fit in this. What weight of this ingredient would give us our carbs, our total carbs? Aren't we in essence kind of solving our problem here? We are, but for each individually, and what we're interested in is a combination. So, but still. Okay, one step at a time. We'll figure it out as we go. So we need to divide our nutrient goal by this. What does that give us? For instance, if we were to do this with our chicken example, we're taking our nutrient goal, which is 20. We're dividing that by 4, which gives us 5. Yes, of course, needed the calculator for that. Okay, so we have 5 portion of 100 grams of chicken. So we just multiply that by 100. By 100, and that gives us our weight in terms of carbs. So max weight for carbs. Max weight for carbs. And then we do the same max weight max weight for fat. Let's just order it the way we've been ordering it for so far. So goals dot fat divided by ingredient dot macronutrients dot fat times 100. All these magic numbers here, I'm gonna have to take care of that later. Const max weight for, what are we missing? Protein equals this dot nutrient goals dot protein divided by ingredient dot macronutrients per 100 grams of protein times 100. Okay. All right. So what did we do with that? This gives us the max weight to not go over our goal. Oh, but we probably want to allow for going over, because the ideal solution might not be under that. It could be considerably over if we want to have the right combination. So let's make it twice as big as that. So let's take the biggest one and just times it by 2. Multiply it by 2. And that'll be our max weight. Pretty sure that any solution that would give us, when we're asking for 22 protein, any solution that would give us like 44 protein would be pretty bad. I don't really see a case where that would be the best solution. Although no, since we're in control of the weight for each ingredient, we really shouldn't have to go much over it. But we could. We could. Okay, is there another way then to restrict this somehow? You know what? Let's make it 5 times. Because at this point, what I really just want is to have some stopping point where the algorithm can go, okay, I've exhausted all reasonable possibilities here. I can stop and give you my answer. So let's do that for now, and we'll come back to it if we feel like we need to change it. So I'm gonna say let's grab, we could make it simpler than that and just add all of them. Yeah, let's do that. Why not? Max weight for carbs plus max weight for fat plus max weight for protein. And again, if not, I'm going to try to keep the same order. So we're going with fat carbs and protein. Is that? No, it's fat, protein, and carbs. Fat, protein, and carbs. Cannot find a max weight. That's interesting. Const max weight. No. Bounds. No. What are we doing? Oh, we're supposed to push this to ingredients max weight dot push. So that works. But let's do it like that. There we go. Okay. That seems reasonable enough. So going through our entire list of ingredients, and we're assigning some max weights for each of the ingredients based on some kind of arbitrary, crazy way of doing this that I've just made up. So now that we know where to stop, we can go ahead and actually try to figure this out. Well, we need to take each of our ingredients. I'll just comment that. I'm going to refactor all of this so that it's more understandable later. But so here we're setting max weight for each ingredient. And here we're going to go over the same list of ingredients. What are we doing? Well, we are starting at 0 for each ingredient. We basically need to go and figure out each possible combination. Okay. This may be more complicated than I thought. Anyways, in terms of using a brute force algorithm, but using something like a hill climbing algorithm, it could work. Let me just think about this here for a second. See, if there's just like 2 ingredients, then it's pretty easy to do. But if we end up with like 4 or 5 ingredients, what would be the algorithm to make sure we're testing each possible combination? And there's got to be an algorithm for that. I just don't know it. Well, it's just a set of loops upon inner loops upon inner loops upon inner loops, and it just gets crazy. Yeah. So if we want to do this with just the 2 ingredients, like Dash was asking, it's not that big of a deal. But I have a feeling that she's looking for something that would allow for more than just 2 ingredients. Let's look at the description she gave us. I have a given set of ingredients. Let's say apples and this chicken. How much of each ingredient should I eat to get as close as possible to my nutrient goals? Yeah. I'm guessing she wants to be able to eat more than just 2 items per meal. Okay, so I have a feeling that we're going to need to go with something else than just pure brute force. maybe something more like hill climbing, which is, or we could even make it just completely random and let the computer go wild and run for a while and just give us whatever output is the best. Kind of a Monte Carlo simulation kind of thing. That works too, and I'm often quite surprised with the outputs, and sometimes they're not the like global optimal, but they'll be very close, or at least a local optimal, which is very close to the global optimal. So that could be something interesting to do too. In any case, this isn't lost. This is going to be useful. This is something that we're going to need too. So this is we're keeping this for sure, because in all these we need to be able to evaluate the fitness of our result, I guess. But this is where we're going to change our thinking here a little bit. I'm not going to try to systematically, go through all the possibilities. I need to find another way to do that. Now with hill climbing, you just pick a starting spot and you look at, let's see, yeah. So you pick a starting spot. So let's say I could, in this example here, I could say, all right, let's start off with trying 100 grams of apples and 100 grams of chicken. Okay, what's our score? All right, and then you would look at, well, let's try 100 grams of apple or 99 grams of apple. And then you would move towards whichever one would have the best score compared to your starting score. And then you would, you'd do that again, just, change a little one thing. And then you'd look at which side would be best, and then you'd move until you reach, well, normally a hill climbing would be looking for, maximizing the score, but in our case, we want to minimize our score. We want our score to be as close to 0 as possible. Yeah, and I'm pretty clear on how that works with one parameter, but when we're dealing with more than one, I'm not too sure. I'm not too sure on the algorithm, because I remember you're only supposed to change just one thing. So I would have to look that up. So that's what I'm going to do, but not right now. Not right now. I'm going to come back to this. And instead, we're going to move on to our coding game puzzle. And we'll get back to this maybe tomorrow. So let's see, maybe I should just commit to here. We'll call this implement score function. Okay. All right. So if you're watching this dash, sorry, we're going to have to get back to you. And this is, funny enough, this is another optimization puzzle or problem we're going to be trying to solve. What are we doing here? Rob is a robber. Clever. He wants to operate a last time in the neighborhood before he leaves. He has been informed about the values of the content of each house of a street, but he is careful, and when he robs in a house, he avoids the 2 houses aside, left and right. What is the maximum money he can make without being caught? Be warned, some houses have been trapped. They have been rated with negative values. For example, for a street of 3 houses with values A1, B2, C3, Rob shall visit houses A and C. He takes 4. Wait. He is careful when he robs in a house and he avoids the 2 houses aside. Left and right. I'm not too sure Oh, okay. So basically he doesn't rob adjacent houses. Right, so A, he won't do B, so he's going to go to C. In this other street, A1, B15, C10, Rob should avoid C and D and visit only B and E. Why? Okay, because if he visits A, then he can't do B, and B's worth 15. It's the highest one. And then he does C, and then he can't do D, and he does E. But okay, so that doesn't seem too complicated. B, C, D. What kind of algorithm would work with that? Let's set up the thing first, and we'll figure it out. So we're gonna get out of here. Yep. I think I have made a code and game directory. Yep. What do I have in there? Lumen. Okay. Let's set up a new one for robbery. Optimization. It's VTS. This is a small command line utility that I've built to set up new projects. Do I want to get repo? I do want to get repo. Okay. And let's just open code, VS Code in there. Okay. Now what we need to do is set up code and game to just open the terminal here. Okay, npm run dev. This will build our TypeScript into JavaScript and watch for changes, so it'll update it as we're doing this. And now I can use my external editor. We want a robbery optimization, not the source, but the built stuff here. Forgot to copy this first. Let's do that. Okay. Upload from local file to code and game. There we go, and now it's going to sync. Live as we're doing this. So let's see. Auto-generated code below helps you parse the standard input according to the problem statement. Yep. And what is the problem statement here? We're getting on line 1 an integer n for the number of houses in the street. Next n lines, the value, house value of the nth house content. Okay, so that's pretty simple in terms of input. In terms of input, it's pretty simple. Constraints. N is smaller or equal to 1, so there's at least one house, right? Oh no, that's the house value. No, that's the, yeah, that's the number of houses, or a maximum of 100, okay? The house value is smaller than 10 to the power of 13, so I think that's like the biggest float number in JavaScript or something. So it can be pretty big. I don't know if that's going to be useful for us to know this, but maybe. We'll see. Okay. So what are we doing here? Oh, read line. Yes, yes, I know about read line. What do I need to do? I need to do const function. Readline is a built-in function in the coding game engine. No, maybe it's just declare function readline returns a string. Yeah, okay. So I have to tell TypeScript about it because it doesn't know where it's coming from. Const n, which is our number of houses, that's what we're getting in the first line, and then we're getting the house values. That's and we're not doing anything with it. We should be at least storing that somewhere, shouldn't we? Or maybe we'll just do our logic in here. But for now, let's just console log that stuff. And house value, just to make sure we're grabbing our inputs properly, and run that in here. See what our output's going to be. Yeah, say we're grabbing the 5 and we're getting our values. And that's our example here. So first we were supposed to get the 5, then 1, 15, 10, 13, 16. Now, I don't know why. What is this 0 here? Parse integers. N I is equal 0, I is smaller than n, I plus plus. That's very interesting. Oh, it's this here. Okay. That's okay. All right, so how do we solve this? That is the question, isn't it? Let's see. We know that we're not allowed to rob any adjacent houses. So what kind of algorithm would give us the best output? I'm thinking some kind of recursive function where we first go and solve if I rob this, then I can't rob this, but I can rob this. Huh. Because the first thought might be, okay, well, let's just go through our list of numbers and go, okay, well, if I start with this one and I rob this, then I skip this one, then I rob this, and I skip this one, and I rob this, and I skip this one. So what's the total? Okay, so for this one, this is my total, and then I do the same thing with this one. If I rob this, then I can't rob this one, but I can't rob this one, I can rob this one. But if you do it that way, you end up like doing the same work many times. It won't be performant, is what I'm thinking. And let's not forget that we can have like 100 houses. Do we have any test cases that have like, yeah, we do, see? Boom. So we kind of need to think about this. I would think, although computers are pretty powerful. Difficult problems. Is there a way to do this recursively? And are we also allowed to, so for instance here, Rob should avoid C and D and visit only B and E. So yeah, we're allowed to skip more than one house. Like the only rule is that we can't rob. If we've robbed a house, we just can't rob the one next to that, the ones next to that. But if we want to skip the next 5, we can. It wouldn't make sense, but how about this? I don't know why, but I'm thinking that this is the kind of problem that we need to like split. Yes, probably. Right? Probably like what is it? Merge sort, the algorithm, I think. Where you first start by sorting just 2 things, then you take those and then you sort them, and would that make sense? Would that make sense? And you would use a recursive function to do that. So, okay, how would that work? We take the first pair and we select which one gives us the most money. Then we take the next pair and we select which one gives us the most money. And we take the next pair and we select which one gives us the most money. And we take the next pair, and we take the next pair, and we take the next pair. Does that make sense? Or should it be 5 and 1, 15 and 10, 13 and 16, or should it be 5 and 1, 1 and 15, 15 and 10, 10 and 13, 13 and 16? Paper, please. And we're gonna make this even smaller to try to figure it out. So more thinking than coding today. So let's say we're just looking at 5, 1, 15, 10. Just keep it simple. Or actually, let's take the first one, the first example that they give us. which is 1, 2, and 3. And they already said that A and C gives us the most money. But how do we know? Just between 1 and 2, 2 gives us more money. Between 2 and 3, 3 gives us more money. Between 2 and 3, 3 gives us more money. Go with 3, and then we can only pick 1. Does that work? Let's take a bigger one. Let's take our 1, 15, 10, 13, 16 example. And between 1 and 15, we'd grab 15. Between 15 and 10, we'd still grab 15. Between 10 and 13, we'd grab 13. 13 and 16, we'd grab 16. Nope. That's not right. That is not right. This is a hard one. I can't see it. It's not obvious to me the algorithm that I should be going for. Let's see. 1, 15, 10, 13, 16. If I were to solve the problem of choosing which one or maybe in sets of 3? See if I can find some inspiration with, I'm pretty sure it's the merge sort algorithm that compares the divide and conquer algorithm. Yeah, that's kind of what I have in mind. Divide and conquer, right? But so do we, okay, so you start with the entire thing, you split it in 2. And then you split that into, and you split that into, and you split that into. And then you further split it. Then you start sorting. You sort those, yeah. You sort the 2 pairs here. You sort this, sort that, sort that, and then what? But right, you just compare them. Yeah, I get it. The thing is, it's the looking ahead and behind that's the problem here. So really our smallest I am stumped, guys. This is hard. Harder than I thought it would be. Like, I mean, I could always, well, I could always try to use some sort of a Monte Carlo simulation. Just randomly try different things, but I don't think that's the purpose here. I know there's an algorithm that'll make it work. It's interesting that this is under the easy category. There might be something I'm missing here. So if we're solving this for just 3, what are we doing? We're starting with the first one. We're saying, well, there's no houses here, so no problem. Then we're looking to the next one, and it's here. So we're obviously thinking, well, B would be better, so I shouldn't be robbing A. So, okay, what if I rob B? Well, I can't rob A. I also can't rob C, but C's better, so I should rob C. And if I rob C, I'm allowed to rob A. I'm just not seeing how it's like the getting back to. That's, how do you break down the problem, isolate, and use. I really don't know. So how about I cheat because I'm stumped. So what's it called? Robbery optimization. Robbery optimization. Solve. Always forget to put this on alarms only. Even filter sorted by first element, filtered by second element, which is not a side by side. See, one exists. Or debugger out. There's one section on the 20 house test that yields a total value of 75. Yeah. Hi there. This is not an easy puzzle. Please at least move it to medium. I'm tempted to agree with that. New players coming into this will be disgusted. It requires some skills to figure it out. Oh, it is in medium now. Really? No, it's back in easy. Yeah. Okay, but we're looking for an algorithm that can help us with that. Enough of the complaining about the difficulty. Now we can do this. I just need some kind of hint. I have an idea of what would work, but no. Nope. This could be it. Yeah, I think it is. Imagine you're a thief trying to steal as much gold from a neighborhood as possible. Consider a single row house. How much you call it in a house. You're able to plan out, but to avoid triggering any alarms, you set the constraint that you won't steal from any two houses that are right next to each other. That's what we want. Let's learn. Let's figure this out. Output 10. 3 plus 5 plus 2. What observations can we make? When it comes to problem solving, it's always good to start with an example that is simple enough that we can eyeball the answer, but complex enough so as not to be trivial. This will be a sanity check against our approaches. Right off the bat, we can notice that we've skipped over 2 numbers between the 3 and the 5. Yes, we have. This means the optimal solution may not always consist of robbing the closest packing of houses we've determined that. We may want to skip over more than one house. Yes, we figured that out. We can also start to make some predictions about time, space, complexity. Let's focus on a brute force approach, which is one thing that I thought we could do, but obviously not ideal. Given that we have to steal from a subset of houses to find the optimal amount of gold to steal, what subsets do we need to test? Brute force. Try stealing from all valid combinations of houses. How? Yeah. Given that we have like some cases that have 100 houses. So what constitutes a valid combination of houses? Any combination that leaves at least one house between. Can you guess which one? Wait. Now that we've established we need to test different valid combinations of houses, this problems starts to look very similar to another problem that uses recursion. Can you guess which one? Modified power set in disguise. Don't know about that. Might seem surprising at first, but so many recursive problems boil down to this pattern because what we're essentially doing is trying all possible combinations of solutions. Here's what that looks like for our previous example. Try all valid subsets. 3, 1, 2, 5, 4, 2. 3 and 2, 3 and 5, 3 and 4. Yeah, 3 and 2. Yeah. 1 and 5, 1 and 4. Yeah. But once we've created all the valid subsets of houses we can steal from, all we have to do is sum up all the values in each subset and pick the one that produces the largest sum. Yes. But if you're wondering how the heck do I set up the recursion to solve this, you can use this high-level pseudocode. Oh, this can actually be useful too for trying to solve the previous puzzle we were trying to solve for Dashiell. For each house, in the neighborhood, you are deciding between stealing from it and skipping the next house, or skipping the current house and making the decision again at the next house. And that's true. Translating that into low-level pseudocode can be solved recursively with the relationship max gold at house index equals maximum of the worst handwriting ever. Maximum of houses at house index plus max gold at index plus 2, house index plus 2, and max gold at house index plus 1. Hold on. House index equals if house index. Okay, yeah, thought we were missing, because when does it stop, right? If house index is bigger than house.length, return 0. Okay. Here's what the code looks like in JavaScript. Thank God. Function house robber recursive takes in our array, steal from house index if index is bigger than return 0, then return the max between our house plus, and then we're recursively calling the, if we're skipping over 1, or simply the next house. Which one gives us the most? Yeah, so essentially it comes down to what I was trying to figure out. You need to basically look at 3 houses at a time. That's what I understand, right? Return steal from house 0. Yeah, because we're starting at index 0. Now let's analyze the time complexity of this approach. Thinking about this naively, testing out all possible combinations of houses should probably seem like a lot of work, especially when the neighborhood is large. Yeah. Let's try it just for fun, though. Actually get some coding going. It's not that complicated. But wait, how is that gonna... Wait. Does that actually solve the problem? Recursive. Yeah, I gotta see this because I'm not. How are we getting our total value from this? That's what I don't get. That's the thing with recursive functions. Sometimes they're kind of hard to figure out. So yeah, we're getting the maximum between our current house and now we're recursively calling the same function. Passing in, what are we passing in? Our house index plus 2. So we're looking at the next... Okay, I think I get it. This will basically accumulate the results from doing the look ahead and then bring it back up. Let's shove that in there and see for ourselves that this is actually working. So we're going to need to put that into an array. Array. Let's just push that in there. We want numbers. Good. So that once that's done, we can use our algorithm. Oh, thought I had copied that. Okay. Type of any because it does not have a return type annotation. You're returning a number, my friend. You happy now? There you go. Okay. So technically all we need to do now is pass in, or call, I mean, house robber recursive with our array. Technically, without any merit whatsoever, having stolen the answer from the internets, this may work. It does. Oh well. Let's try it with all test cases. Well, no, let's go one at a time because I think it's going to be... So this runs pretty quickly. Oh, a little longer on 9 houses. 1 house. 20 houses. Not bad. 50. Ah. Ooh. It's taking a while. Process has timed out, and this is the problem. Now we're going to need to optimize. So here's what we're going to do. I'm going to spend 2 hours already. I need to stop, but I'll do a bit of reading up on this algorithm. Think about it, and tomorrow we will optimize this algorithm so that it runs faster and we're able to pass all our test cases here. So thanks for sticking around. I think there was a bit more thinking than coding today, but I guess that's what you often have to do when you're solving some interesting problems. All right, so see you guys tomorrow at 10 a.m. Eastern Daylight Savings Time.